Okay, good morning. So let us continue the lesson. That is actually a very important lesson. It's section 2.3 in the book. If you remember, we talked about the notion of the derivative. We learned that, of course, this concept is very important. And then, unfortunately, I gave you some examples that you saw probably and remember that the process of finding the derivative is a little bit lengthy, yes? And that was actually the same problem that mathematicians were facing. So if we have a complicated function and if you want to find the derivative of that function, it is a very long process, okay? And unfortunately, might be we need the derivative of different functions. We have to find a way to make it easier for us. So let me write a formula here for you. Do you remember I told you that f prime of x is the limit of f of x plus h minus f of x divided by h goes to 0, yes? Yeah, that is the formula for the derivative of a function. If you remember, I wrote it first for a number, then I gave you an example. If you remember, I told you that if I am a little bit problematic in my mind, I will change that number from a number to another number, then that would be better for you to solve what problem once for every x, and then if I change my mind, you can replace that x with the number that I will give you. Okay, and then we use this formula to solve some problems. But now we want to face the problem a little bit more systematically. Then I want to ask your opinion. Assume that you are a mathematician. You realize that this notion is important. And then you also know that this is more or less a very lengthy process, especially if the function involved is a complicated function. Okay, and now you want to find a way to study this concept. What is your suggestion for us to do? Because you know that how many functions are involved in mathematics, in the whole mathematics there are infinitely many functions. It is clear that I cannot find one formula for each function. It's not possible at all. So we have to find a way that we can solve our problem, yes? So do you want to say something, Rocco? Yes?
Yeah, you could just test around, see if there's an exponent, see what happens, and try to find rules you can use shortcuts.
No, but tell me something practical. Yes? So what do you mean by shortcuts? Yes, of course, one way is, but I can promise you there are no shortcuts. Do you remember the examples from the previous session? Yes? That they are actually very simple functions, by the way. If I change them a little bit, then calculating this limit, the process of calculating the limit becomes very, very lengthy, and I would tell you that sometimes it becomes impossible. We have to do it a different way. But for the time being, don't go so advanced. Just try to see that I want to solve my problem. I have infinitely many functions on my table and the world of mathematics, and then I want to solve them systematically. What is the first thing that you do? You have a mess of functions in front of you, and you, in principle, of course, if you are doing some problem in physics, you don't care about all diversity of functions which live in mathematics, because a physicist might be interested for just a particular function coming from the world of physics. For example, if Newton probably was interested in finding the gravitational force between two masses, yes, if this mass is little m and this mass is capital M, and then he realized the force acting here is a constant called g and then m times m, and if I call this distance, for example, between the centers x, this becomes x squared. And then this number is a constant, then what was important for Newton was just this function, a constant divided by x squared. So So might be you say that, okay, Newton didn't care about all diversity of functions in mathematics. He was only caring about this. And actually this is why Newton even didn't bother to systematically think about derivatives. Because he was interested more or less about these functions. And this is just one single function. He could do it once for all and then use it over and over again. But in the world of mathematics, of course, even in physics, we have different functions involved, which probably was not known that time. But anyway, what I'm telling to you is that you have a mess of functions in front of you. Consider all possible functions, and then you want to study them, study the derivative of them. What is a wise way to do that? That is very natural, yes? If you enter a library with a lot of books piled up at some point and you want to study them, what is the first thing you do? Yes, Hussein?
You organize them.
You organize them, yes? So first you organize them. What does it mean? Organizing means, for example, you might put the physics books in one shelf, mathematics books in another shelf, so you separate them. That's exactly the way that we have a mess in front of us. We want to do something, we have to organize and categorize them. So it means that we need to think, instead of each particular function, we can think what type of functions we have in mathematics. Yes? So then you start tabulating those functions. So what I want to start today, I want to draw a table for you here. You will not be able to finish it in high school. You will continue finishing it in the university, okay? And one part of it we want to study today, okay? And then one of the main parts of this lesson is to completing this table. Okay, completing this table for a function and its derivative, and this will be given to you in the formula sheet. So what I do, I write f here, and I write f prime, meaning the derivative of this. Okay, let us start with this one. If I ask you what is the simplest possible function that can happen in mathematics, what is that function?
X to the 2.
No, it's much simpler than that. Don't go too fast. The simplest possible function. Yes?
X plus 1.
No, it's simpler than that.
X.
Simpler than that.
X equals 1.
No.
Y equals
Constant function.
Y
A
equals
constant function is actually the simplest possible function. You see, I start from f of x, and I would write it as, for example, 5. This is a simplest possible function. Not just this one, the category of constant functions. What do we mean by a constant function? It means that you have a machine, okay? So you send x in, f doesn't care what you send in, it gives you 5 back. Yeah, if you want to imagine they are dictators in the world of mathematics, they don't care what you demand, they will say that the answer is always 5. Yes, that's a constant function, and that is the simplest possible function. Any number, C. I would call it C for constant, yes? So I agree, hopefully you agree that this is simpler even than x. Yes, x, if you draw the graph of x, it would be a little bit inclined, but if I draw the graph of y equals to 5, it becomes just 5, yes? And constant functions are simpler than even y equals to x function. Because you don't need to bother. Whatever this number is, the answer is 5. So it is, even I would say it is simpler than even that function. Because at least here, if I give you 1, this will give you 1 back. If I give 2, it will give you 2 back. But here whatever I send in, you really don't need to bother at all. The answer is 5. So this category of constant functions are probably the easiest possible functions that we can imagine. Yes? So instead of studying this in particular, let me study this in particular. So in general, C is a constant. C is any constant. We want to write this as our first function here, a constant C, and then we want to understand its derivative. Yes? Okay, what is the graph of a constant function? For example, what is the graph of y equals to 5?
Straight line
A straight line.
that crosses
a horizontal, a straight line that passes from the point 0 and 5, yes? So if I ask you, of course that is also a little bit strange, but let me tell you that if you have this, if this is the x-axis and this is the y-axis, okay, and then this is 5, this is your line. Of course, this might be a little bit strange. If I ask you what is the equation of the tangent to this line at this point, by the way, that's good to understand. Good to know that this is also the same line itself. So if I ask you what is the line tangent to this line at this point, you should say the line itself. And if that's the line, the derivative is the slope of the tangent line, which is so you see, if I tell you this graph, if I ask you what is the derivative at this point, you draw the tangent line here, yes? You draw this tangent line, and then you determine the slope of this line. Whatever this number is, you would say that the derivative at this point is that number. Now, according to this, if I ask you what is the derivative of this constant function at this point, you would say that I first draw a tangent line to the graph at this point, which coincidentally becomes the same line itself, and then measure the slope of that tangent line, which is no, the slope.
Was it undefined or 0?
No, it is 0. A horizontal line, it is the slope is 0. So, okay, I change my mind from this point to this point, but the slope will not change. So, from geometrical point of view, without this formula, you know that the derivative of a constant function at any point on it should be 0. Okay, so that is the simplest possible one. But of course, I want to do it algebraically because understanding the formula is also important. Yes?
You said that like a tangent intersects like one point of a graph.
No, might be this graph will go higher, and then this will continue and intersect here. So this is both a secant line and a tangent line, but it is tangent here and secant here.
Okay, but in this case, it's secant at
No,
all
it is in
points.
this case. I agree. This is not exactly according to our intuitions. I wanted to give you the feeling. If that's not working for you, you have to use it, the rigorous mathematics. Okay, so I will prove. This is why I want to prove this using this. Okay, now, but let me draw this diagram for this. Okay, so if I want to draw something like this for this function, I would write the function f here. I will send whatever I want to, call it x, but this function, independent, regardless of what I put in, it will give me what? This function, c. Okay, so that is the diagram that you should have in mind. Okay, now let me calculate this derivative here for you. So the derivative f prime of x for this function that you see in front of me is equal to the limit h goes to 0. Okay, I want you to fill it up for me. The denominator is of course h. There is a minus sign here, so let me put it here. Help me to write. What can I write instead of f of x for this function? C. But what can I write for this function? C again, because I told you that it doesn't care about the input. The output is C always. The input is x plus h. It is different from this input, but this function doesn't care. It becomes just C itself. Yes, is that understandable? And then if I ask you what is C minus C, it is 0, so the limit is 0. And that is actually the mathematical way of convincing yourself that the derivative of a constant function is equal to 0. So this is not that fun, but I have seen students sometimes make mistakes. Constant, I mean constant. Okay, what do I mean? So if I ask you what is if the function is 5, if I ask you what is the derivative of this function, the answer is 0. So the good point is this. So let me give you another one. Pi, do you know that this famous pi number? So what is the derivative of this function? It's also 0. So pi is just a constant number. We know pi, and this becomes 0. Okay, I don't know. If I give you f of x equals to square root of 2 plus square root of 2 divided by 3 minus the square root of 2, if I ask you what is the derivative, you can answer immediately. The answer is 0 again. But it doesn't matter how I write my constant. As soon as it is a constant, it's a constant. So let me just tell you another one. F of x equals to logarithm of 5 plus pi. Yes, that's it. If I ask you what is the derivative of this, again 0. Because it doesn't matter, this is a constant, 5 added to it, it's a constant. Log of a constant is a constant at the end, and then the derivative is 0. So it doesn't matter how your constant is written, if you are convinced that the function is a constant function, then you can say that the derivative is equal to 0. And if I want to draw, by the way, if this function is a dictator, but then actually the derivative is even worse. Yes, why? Because the constant function, the derivative is always sending everything not to any number, to only 0. So if you have this scenario, that you are sending x inside and getting a constant back, the derivative will send x always to 0 only. Yes? Not any constant. Okay, so we are done with this row, and we had some examples. I think that is not very big deal. Okay, and then we want to increase it to another, we want to increase the level of difficulty. Okay, now after the constant functions are finished, now I want to hear from you. What function do you want to put there next? Yes?
F of x equal to x? Or
X is probably the simplest one after that. This is the way that the book has done it, and I want to do it because if I want to prove it, it is actually beyond the scope of the lesson. But I want to try to convince you exactly the way that book has followed. Okay, so you have to be patient. So that's a good exercise in the definition of the derivative. So you told me that the next function that we want to probably investigate is this one. Yes, because this is probably the simplest one after this. So what should I do? I would write f prime of x. Let me ask you to make it a little bit shorter. So this is h going to 0. It is h. And then what is f of x? So this negative sign. F of x is x. Okay, can you tell me what is x plus h? F of x plus h?
X plus h.
X plus h. Because this is a simple function. Whenever what you put x, it gives you back the same thing. That is, by the way, called the identity function. It doesn't do anything on the number. It gives the same thing back. So if I send x plus h into this function, it will give you what? X plus h. So if you want to draw a diagram for this, you send x, whatever you want to, it returns the same input back. So now that I am sending x plus h in, it will give me x plus h back. Yes? Understandable? Yes or no?
Yes.
And this x and x are gone. So this becomes what? 1. So the derivative of x is equal to 1. Yes? But let me, now if I ask you what is coming next, if you want to increase the level of difficulty of this one a little bit, you have two ways. You can say that I add a constant to it, or I can increase the power. Okay, adding a constant, I will talk about this later, but let me increase the power. Okay, so this is why I want you to see. Of course, this is not a way, a mathematical way. It's good, but not very convincing. So let me now change my function to x squared. The way that we have to do it, because you do not know some other theorems, we have to do some of them to find a feeling for the pattern and guess the pattern and rely on that when your teachers say that this is the correct one. Yes?
I'm sorry about that, but how you told us the input on this last one, with the x, f of x equals x. How is the input any different? Because shouldn't it be the same?
No, it should be the same as the input.
Because why? How does that work? It's not like the last one with the f of x equals 5 became like 5x became 5x.
No, f of
That's an
x is
output.
equal to x.
Yeah, exactly.
When I send x in,
Yeah,
it
you
gives
get an
me
x
the
back.
same x back.
But
What do you
earlier
mean, why?
when we had a 5 instead of the x, and we put in something, then we got an x and 5 as an
Yes.
output, right?
Yes.
How did we get an x plus h here?
No, I don't understand your question. The function is the function that whatever you send in, it gives you the same thing back.
Yeah, so
Now
how
you
did
are
we get-
sending x plus h in, so it will give you x plus h back. Yes? That was different from f of x equals to 5. F of x equals to 5, you send x in, but it doesn't care what you send in, it gives you 5. Yes? Okay, so let me solve that problem for this one as well. So what we have to do, we have to calculate f prime of x. Because the formula is here, let me not spend time on it. So, and then immediately start calculating things. So can you tell me, so there is a negative sign here. On the right hand side, what should I write? I should write my f of x. But what is f of x in this case? X squared. Okay, can you tell me what should I write? If I want to draw a diagram for this, you send x in, what do you get back? It squares it, and it gives you x squared back. Now what you are sending in, you are sending x plus h. The function will do exactly the same thing for the new input. So what it will return to you?
x plus h squared?
Squared. Okay? Of course, this needs a little bit of work, so we have to do it now. So then you have enough experience of that, so I square it using the squaring pattern. So it becomes x squared plus 2xh, and then plus h squared, and then I have minus x squared. X equal h goes to 0. And then you see that this x squared and that x squared are cancelled. Between these two terms, I can factor an h out. This becomes 2x plus h, and then divided by h goes to 0. And then you know that I am on the safe side, I can remove that. And what is left for me is 2x plus h. When I send h to 0, the answer becomes, tell me? 2x. Okay, so let me put these things in a box, yes? So when f of x was x, the answer was 1. When f of x is x squared, the answer is no longer a constant, the answer is 2x. And if you don't mind, exactly like the book, let me do it once more for x to the power of 3. Yes? So let me just do that. This is not, by the way, the real way to do it. The reason that I have to do it case by case, because I want to convince you about a pattern that you will see by comparing them. And the reason is, I will tell you why the reason, what is the reason that you cannot solve it in full form. So let me make it a little bit harder, x to the power of 3 this time, yes? So this is a function, you send x in, and it will raise it to power 3 and gives it back to you. Okay, now I want to calculate the derivative of this function. So what is the answer? So the limit h goes to 0 as usual. The denominator is h. You have a negative sign here. You have to write your x to the power of 3, and then you have this 1 to the power 3. Please let me know if you don't understand what I have written here. I am using this formula for this new function. I'm telling you that this is what you have to calculate. Yes, is that understandable for everyone? But now you understand why the problem becomes harder and harder. Because if I start increasing the power, it was very simple here. It was a little bit more problematic here because I have to expand that. And if I raise the power to 3, this is not the problem. The problem is here. I have to raise it to power 3 this time. And then it means that I have to multiply it by itself 3 times. Or in Math 5, if you continue to Math 5, we have a formula, a long formula for raising this to any natural power, not 3, not 4, for any number. If you knew that formula, then we were able to prove this not in this form case by case. We could just tackle the hardest, the most general one. But here, I don't want to do this. I want to exactly follow what is written in the book. So we have to expand this one because might be many of you don't have it in your memory. So, of course, this formula is also given in the formula sheet. So let me just expand this. So I come here, and I would write x plus h to power 3. I would write it as x plus h to power 2 multiplied by an extra x plus h. And then I know about this. It becomes x squared plus 2xh plus h squared. And then I multiply it once more by this, and let me expand and simplify. It becomes x cubed plus x squared h, and then I will multiply this one, 2x squared h plus 2xh squared plus h squared x plus h cubed, yes? And then I can simplify it even more. So x to the power of 3, this one and that one are similar, so it becomes 3x squared h. These two are also similar, so it becomes 3xh squared, and then finally h cubed. So I hope that you agree that if I increase it to power 4, then it becomes more problematic. I have to multiply it 4 times. This is why at this level you cannot solve it in the full general form. But that would be the end of this. I want to check these things and try to guess a pattern for that. Yes. So here I will continue limit. Instead of this one, I put this expression in. So it becomes x cubed plus 3x squared h plus 3xh squared plus h to the power of 3 minus x to the power of 3 divided by h goes to 0. And then you see that this one and that one are gone. And then you can see that I have h in common, so I can factor it out. It becomes a 3x squared plus a 3xh plus h squared divided by h. h goes to 0, yes? And then this h and that h are cancelled. Okay, can you tell me what will be the answer? Yes, this one will be 0, this one 3x squared, yes? Okay, so if I want to put something in the box, so if the function was this function, then the answer will be this. Yes? Okay, I think, yeah, because it would be very lengthy and that is not fun if I want to increase it. So what we have, if I have f of x equals to x, the derivative was simply 1. So if I ask you what is the power here, the power which was not written was 1. Yes, let me write it with black, yes. So x to the power of 1, even though we don't write it 1, but the derivative was simply this. When I had f of x equals to x squared, then the derivative was 2x. And then if I raise it to power 3, the derivative is 3x squared. Okay, now assume that I will increase it to a generic power x to the n, where n is a natural number. This means n belongs to the set of natural numbers. It means n is a natural number. Okay, can you tell me, if I continue this list, what should you expect here? Yes, Gasha?
nx to the power of n minus 1.
1, exactly. So that is the pattern. Yes, you see here, 1 goes down, even though here it was x to the power of 0, which we haven't written it because x to the power of 0 is 1. But that's exactly the same pattern. 1 goes down, x to the power of 1 unit less. 2 goes down, x to the power of 1 unit less becomes 1. 3 goes down, x to the power of 1 unit less. So if you have x to the power of n, even though it's not a mathematical proof I am selling to you, but I hope that you agree that this will be the case in the general. But the problem is still not finished. And the problem can be quite harder. Because I am only caring about natural powers. Yes? So this is why I don't want to write the formula yet. What happens if I want to give you x to the power of 1/2 and then ask you the same question? Yes? This is no longer a natural power. Yes? Natural exponent. And I hope that you agree with me, this might be quite different. Because I will tell you why. Let me try to think about this new problem here. So apparently we are happy. We were able to somehow find or guess the correct formula for the derivative of this function, but there is one important constraint so far, and that is n is a natural number. Let me relax this condition. Before, by the way, going to fraction powers, what comes first? If you remember when we are studying powers, we studied in positive natural powers first, and then before reaching to fractional powers, we studied something before that. What was that? Yes?
Negative powers.
Negative powers. So instead of jumping immediately to this harder problem, let us jump to negative powers. Yes? Let us see what happens for negative powers. And of course, what is the simplest negative power over here?
10.
No, negative power.
1 power minus
Negative 1, yes. So let me change this to x to the power of negative 1. Okay, so what do I mean? I mean, let us consider this function. F of x equals to x to the power of negative 1. Of course, you usually don't see it in this form. How do you see it? In books, instead of saying x to the power of, you write 1 over x. But of course, 1 over x is another name for x to the power of minus 1. So let us keep it for the time being here. Because I want to find a pattern. And I want to write 1 over x in that form. So I want you to understand what is happening. Okay, this function is a function. I send x in. It will give me the reciprocal. But there is some limitation for the input in this case. What's that limitation? I can, in the previous functions, I could send everything what I want to in. But here there is one exception. I cannot send 0 in. Because then it becomes 1 over 0 and it is undefined. So 0 is not in the domain of this function. But except 0, I can send whatever I like to. Okay, now can you tell me, how should I write f prime of x? I want you to help me to write that, okay? This copy-paste part, I do it myself. So limit h goes to 0, and then you have h, and then you have a negative sign. On the right-hand side, what should I write? X to the power of minus 1. What should I write on the left-hand side of this negative sign?
X plus h to the power.
X to the power, yes, exactly. X plus h to the power of minus 1. This would be my function. Yes, this would be the limit that I want to calculate. But the point is that even if you go to Math 5, we don't have any formula for expanding this for negative powers. That formula that you study in Math 5 only works that if you have a natural power. For natural reasons, yes. If I give you h plus to the power of 3, you can't write it in principle 3 times and multiply it. But if I ask you x plus h to the power of minus 2, you cannot write it 2 times or negative 2 times and multiply it. Yes? So what should I do then? Yes? Yes, we have to write the reciprocal. So it means that, to write it in the positive form. So I can write it as 1 over x plus h minus 1 over x, and then it becomes a little bit more complicated, but this is one of those problems you solved in chapter 1 when we were dealing rational expressions. And that is one rational expression. We have to simplify that. So I don't know which one. I have told you this several times. I have a fraction. In the numerator, I have extra fractions. So I would say that they are partial fractions. I would prefer to rescale the whole fraction by multiplying the numerator and the denominator by this factor. Why is that good? Because if I take the numerator, so let me multiply the denominator first. The denominator is simple. H goes to 0. I multiply the denominator by this factor I mentioned right here, yes? But can you tell me, if I rescale the numerator by that, what will be the first term? When I multiply everything by this factor, x times x plus h. When you multiply this here, what will happen? Yes, it becomes x. X plus h will cancel that one. X is left, so I would write x. Then what will happen for the next one? Okay, but if I write it in this way, it is wrong, yes?
No, but
You have to put a pair of brackets around. But what I have to do, now I remove the pair of brackets, it becomes x minus h, and then I have h, x plus h goes to 0, so then this x and negative x are cancelled, so let me rewrite it once more in this case. Minus h divided by h, x plus h goes to 0, but then I'm immediately able to simplify these two. Let me write it once more. The numerator becomes negative 1, the denominator becomes x plus h goes to 0. So what is the answer now, can you tell me? I'm sending h to 0. Yes?
Minus 1 over x squared.
Yes, exactly. Because if I put 0, this becomes x, multiplied by an extra x here, it becomes x squared, and I have minus 1. Yes? But now, because I started with a negative power, let me write it back into the form of a negative power. Of course, from now on, it's not compulsory because I want to find the pattern. I would write it minus 1, and then I bring it up. It becomes x to the power of negative 2. Yes? Usually we don't write this minus 1. I intentionally write it. In principle, we should just write minus x to the power of minus 2. But this is intentional. And then, let us see, you see that immediately comparing this one with that one, even though the process was quite different, you see the process of x to the power of minus 1 was quite different from the process of x itself. But the pattern is the same. The nice thing is that, again, this minus 1 goes down. It becomes minus 1. X to the power of 1 unit less. It means minus 1 unit less. What will happen? It becomes minus 1 x to the power of minus 2. You see, that's exactly what you get. So even though that was a very thing, we are very lucky actually, even though it could be completely different rule, but the good point is that the rule is exactly the same as for the rule of positive integers. Now, apparently, of course, if you want to convince yourself, and I ask you to do it once for yourself, so I would, if I were you, I would start with this function, x to the power of minus 2, and then do this one. Of course, this would be very lengthy, more than this, not very, but yeah, a little bit more than that. And then you have my words on it. The same pattern will apply, but you need to do some calculations to convince yourself that the same rule will apply. So it means that if the same rule applies, can you tell me what will be the answer? If you trust me on that.
Negative 2.
Negative 2 goes down. X to the power of 1 unit less, which is?
Negative 3.
Negative 3. Okay? But still the problem is not solved quite yet because there are other kind of powers involved in the problem. And that is the title of the lesson, power functions, yes? We want to talk about power functions. So we learned for positive integers, we learned for negative integers. Apparently I was trying to convince you more or less the same pattern is working. But now let us now jump to fraction powers. And let us see that if we have to change the rule for fraction powers or not. Because this is something completely new for you. I want to listen and I want to do it because it is in the book. Okay? Okay, so let me clean this. And now we want to do it once more for this case. So I want you to understand why I have to repeat it. Could you understand why should I repeat it for x to the power of -1? Because of 1 over x plus h, the process of simplification totally changed. And it was just a miracle that the pattern will survive at the end. It was not very clear from the beginning. And now you will see the process here will also totally change. Okay? So if I start with this function as a representative for fraction powers, let us see what will... By the way, this is not a standard way usually. What do you see in literature instead of x to the power of 1 over 2? Square root of x is the more familiar way of writing. But I have written it in this form intentionally because I want to see that if the fraction if this exponent is a fraction, what will happen. Okay, so if I wanted to draw a diagram for this, f, you send in x, and then what you get at the end, x to the power of 1/2. Can I send any number that I like into this machine? No, I have to keep non-negative numbers, because if I send a negative number and x negative number, square root of negative number is not defined in the realm of the real numbers. Okay, so now let me write f prime of x. So what is f prime of x? It becomes the limit h goes to 0. I have a negative sign here. I write x to the power of 1/2, and then I would write x plus h to the power of 1/2. Make sure that what I have written you understand. Is that understandable for everyone? Yes? But now you see that I have another problem. If it was 2, I can expand it. If it was -1 or -2, I can bring it down and expand it. But if I have fraction 1 over 2, I cannot expand it. Even if I bring it down, I make it worse because it becomes negative. So it means that the process is totally changed. I want you to understand this. Okay, so how should I do this? This is what I want you to learn. And that is exactly a problem that I mentioned at the end of the last session, if you remember. I asked you to solve it. But anyway, if you haven't done that, you can learn it here. So, the thing that we do here, we write it as a square root form. So it becomes square root of x plus h minus a square root of x, and then h goes to 0. The reason that this is problematic is because this h is in this denominator, and this is held captive by this square root, yes? I want to get rid of this h in the denominator, but there is no way for me to simplify this h with that h in this form. So I need to think a way to make this h free, so that somehow might be that I am able to simplify that h with that h. This is the trick I want you to learn. It's a little bit strange if you haven't seen this before, but you need to get used to it. If I want to get rid of this h, if I want to make it free, I have to get rid of these square root signs somehow. Yes? And of course, what can I do? I cannot take this away, or I cannot square it, because this is not an equality. So what I have to do, I have to rewrite it in a way which is equal to this one, but I find a way to get rid of this square root. So can you tell me what to do? I want to get rid of this square root by some way. How should I do that? Yes?
Conjugate pattern?
How?
Well, you could multiply on the domain.
Numerator and the denominator,
Yeah, exactly.
by the conjugate. Exactly. Thank you. This I want you to learn. So you see, I have repeated this, and I put a multiplication. Do you agree that if I multiply everything by 1, it will not change? Yes? I multiply it by 1, but in a fancy way. By multiplying it by this very strange, apparently strange thing. First of all, I want you to understand this is legally done. What do I mean? If I ask you what is another better name for this fraction, what is the answer? 1. And if I multiply my fraction by 1, it will not change. So this equality is actually true. Yes? So this expression is more complicated, but this is exactly equal to my previous expression. Yes? Is that understandable for everyone? This trick you need to learn. So you multiply by the conjugate pattern of the numerator. And now, the answer is very nice. Why? You will see why. this becomes the limit. Don't worry about the denominator, just multiply them formally. Just juxtapose them, put them next to each other. So h times square root of x plus h plus square root of x. That's it. But in the numerator, when I multiply this by this, I immediately detect a nice pattern. Yes? What is the pattern? It's the conjugate pattern. I did it intentionally to make a conjugate pattern. Because the answer will be the first one squared. Let me be patient this time and write everything in detail. So this becomes in this one to power 2 minus the second one to power 2. Yes? So do you see that? By this trick, I was able to make this h free. But you might say that, okay, I have another h which is now held captive, but this will work. You have to be patient and see it will work. And h goes to 0. Okay, so what do I do in the numerator? In the numerator, I can use this power of 2 to get rid of this square root sign. So this becomes the limit x plus h minus this one to power 2 is x divided by, don't multiply the denominator. I mean, that's a multiplication, but keep it like this. Don't expand it. Because the goal is not expansion. The goal is to get rid of this h. And this will happen for you right now. You see, this x and x are cancelled. Let me be patient and write it once more. It becomes h over h square root of x plus h plus square root of x, and h goes to 0. And now you see that that h, which was in the numerator and held captive, now is free. And there is another h in the denominator that I can cancel it out. But this h will survive, but that is not a problem. You will see why. So what is left for me in the numerator is 1. What is in the denominator is 2 square root signs. One of them is x plus h plus square root of x. But h goes to 0. Okay, but now this h is no longer a problem for me. Yes? Now I can put h equal to 0 without having any problems. But I couldn't put this h equal to 0 in the beginning. But this h doesn't make any problems. What's the answer? If I put h equals to 0?
Square root of x. Or
No.
Do you mean the whole thing?
Yeah.
Oh, 1 over 2.
2 is square root of x. Because if I put h equal to 0, if you want, I can write it. Yes, you are right. Let me write it 2 times. Instead of h I put 0, it becomes square root of x. But this is another square root of x left. But nobody writes square root of x plus square root of x because there is a better name for that. Yes?
How did you get from the conjugate pattern to just x plus h minus x?
Okay, so when you raise it to power 2, this is square root sign and these two are cancelled.
Okay.
X plus h is left. And for the next one, x is left. This becomes x plus h minus x.
Right.
Yes. Is that understandable? So it is a little bit, it seems strange, you see. So if you see this was the diagram of my function. This was the diagram of my function. If I ask you to draw the diagram of my derivative, what do you say? You say, I send x in. What does it return? It returns this one back. Yes?
Just have the last one when h disappeared. What happened?
No, I'm sending h to 0. I'm supposed to put h equal to 0, but I was not able to put h equal to 0 in the beginning because in the denominator I will get 0 and I will have problems. So I was finding a way to get rid of this h in the denominator. But the good candidate for getting rid of this h is to make this h free and it will work for me. And using this one, I did it actually, yes? Okay, so you see that was the diagram for my function. The diagram of my derivative is this one. I want you to memorize this formula. I don't know, in Swedish formula sheets, this is always absent. But that is extremely important. I really recommend you to memorize this formula. So the derivative of square root of x is 1 over 2 square root of x. It's good to have it somewhere in your notebook. Okay, it's extremely important formula. Okay, but important formula, I mean that it happens in exercises a lot. Okay, but that was not my goal. My goal was to discover the pattern. Yes? Do you think, so what was the pattern for the time being? You see, if I have this, I learned that the pattern is taking n down and then x to the power of n minus 1. I learned that it worked for positive natural numbers and, positive integers and negative integers. And now I am jumping to fraction powers. Apparently it seems that I have problems and it is not following the same pattern. Yes? Because the form was a little bit more complicated. But if you think wisely, that is the same pattern again. Why? Because 1 over 2 square root of x has another name, even though we don't use it usually, but we can write it as 1 over 2 x to the power of 1/2. Yes? And then I can bring it up. 1 over 2 is 1 over 2, and I can bring it up and write it x to the power of minus 1 over 2. So if I say that this is my derivative, I am also right. This is the derivative, but I can rewrite the derivative in this form, even though we usually don't do it, but here I want to do it because I want to convince you that is exactly the same pattern happening here. So assume that you want to use the same pattern here. What do you write? What do you write? 1 over 2 goes down, and then you write x to the power of 1 unit less. Yes? If the pattern is as before, if you follow this pattern for this one, you will get that. Is that understandable? But what is 1 over 2 minus 1? Negative 1 over 2. And then if I write it, it is 1 over 2 x to the power of negative 1 over 2. And that is exactly what I got for derivative. So apparently it seems that the same pattern also works for fraction powers. Yes?
What if it's a cubic root?
Yes, that would be hard. I have some videos on my YouTube. I will put the links here. If you are interested, you can see those videos. But you understand that if this is cubic, then I will be in big trouble. Because this becomes 1 over 3, 1 over 3. Then it becomes the third root. Conjugate pattern will not work for the third root. You need to find something similar for the cubic root. And then if that is not finished yet, I can raise it to 1 over 4. I can raise it to 1 over 5. So I need formulas over and over again. So this is not the systematic way to do it, but at least you have this is enough for you to understand where the problem lies. Yes. If I increase the exponent to 1 over 2, 1 over 3, decrease by the way, then this becomes much harder and harder. Okay. But at least you have some feeling. You have to have some trust on me here. I would say that it doesn't matter whatever I put here, x to power of any constant, the same pattern will follow. Okay, so C, extremely important to understand that C is a constant. I am using C for constant, yes? So here, C is a constant. So C, a constant. In the following table, a constant. Capital C, or I can make it little c. So to be consistent. So C is a constant. So what does it mean? It means that if I ask you to differentiate this, if I ask you to find the derivative of this, you don't know. And you have to wait for university to know what to do. The reason is that this function is not that function. So you are not allowed to say to yourself that x goes down and then I write x and then this x minus 1. This is totally nonsense. Yes? So be careful. This formula only works if x is in the base and a constant is in the exponent. Even if, for example, if I ask you, do you know the derivative of this according to the formula? You would say yes. If I say, do you know the formula for 2 to power x? Still no. We will also study this one this year. Okay? But this is not following the same rule. This function is called an exponential function. This function is called the power function. What we have learned so far is the derivative of power functions. Yes? Is that understandable? Yes or no?
Yes.
Okay. Okay, but don't think that this problem is boring. We can have a diversity of good functions that you can solve using only this formula. I want to give some flavor for it, okay? So what you expect in coming lessons is to make this table more complete. Yes, that is the type of the lesson that you should expect. And that's an extremely, and I told you that. Some part of it will be left for Math 5 and some part of it will be left for the university if you join some technical or math, physics, computer science or something like that programs. Yes? Okay. So let me give you an example. This is very, very important. Example important. So by the way, let me tell you something. If you are a little bit disturbed about the complication of calculations, you don't need to be worried at all. None of them of this type will be in the exam. So what you need to know is that the conclusion of all what I have written on the board is just this simple formula. So what I give you a function, if I don't ask you to do it from first principles, if I ask you to do it from first principles or by definition, you have to use the limit process. Yes? But if I don't do that, you are allowed to put this table in front of you, which will be given in the formula sheet, and then you will be able to solve it using this formula. Yes?
But there is a but we do still need to like memorize the limit, as the derivative in the limit form.
In principle, I don't know. I recommend you to memorize it.
Yeah, no, for the soul of
Not only for the soul of that, because every time if you want to refer to the formula to write something, it is really distracting.
But,
Especially for these famous things, you really need to use your memory. Yes.
okay, but during the test, we're not gonna actually have to like write it in a question or use it. We just memorize the rules. It's what you're saying.
Yeah. If you have it in your memory, I don't care what you do. I just want you to do the derivative. Okay. So, but I just want to tell you there are two types of questions in the exam. One, I explicitly mentioned use the definition of the derivative to find the derivative. Then you have to do it using the limit process. Even if you solve it using this and your answer is correct, you will not get any points for that particular question. But forget about that. If I give you some functions and I ask you find the derivative, full stop, then it is much, much better to use these formulas because they are very fast. And sometimes if you want to solve those problems using the limit, it is impossible or too complicated. Okay? So now let me just tell you what is here. By the way, I can write find the derivative, or I can use the English word differentiate each function. Differentiation is the process of finding the derivative. So the derivative is the product at the end. Differentiation is the process to go from a function to its derivative. Or you can say find the derivative. Okay, let me start with questions. So if I ask you what is the derivative of f of x, so x to the power of 5. So the answer is simple. You have the formula in front of you. So what is the derivative? Do you think this is one of the formulas in my table? Yes. The answer is yes. So you compare it with the second row and you immediately realize C is 5 in this case. So I follow the rule. What is the answer? This one I want you not to do it, okay? In principle, you should probably write this, but I really want you to do it very fast in your head. Okay? So just jump from here to here. Write the answer. Okay, now let me do number 2. I will give you this function, f of x equals to x to the power of 2 multiplied by x to the power of 5. And I ask you to differentiate this function. I don't know, I have seen some students start inventing new rules. They say that, okay, this one, I write it as 2x, and this one, I write it as 5x4, and then it becomes 10x5. Okay, please write it down and cross it over. This is not possible, okay? So you only know if your function is one of those functions in the table exactly. Even though this part was exactly in the table, c is 2, and this part is exactly in the table and c is 5, but there is no guarantee that if I multiply two functions and I want to find the derivative, I can do them separately. So this is the new rule that if you are inventing, and then you see that in Math 4, this is not the correct rule. The correct rule of that is more complicated than that. Okay? So what I have to do, can you tell me? So if this is not possible, either I should leave it or I have to do something with it. What can I write for f of x?
X to the power of
7, yes. And then, is x to the power of 7 in my table? Yes.
Yes.
C is 7 in this case, and do it in your head. What is the immediate answer out of it?
7x power of
6. That's your answer. Yes? And now let me make it a little bit nicer by combining with the square roots or surd signs, yes? So you can have f of x. Let me write it as x times the square root of x. I want to differentiate this function. So what can I do here? This formula, this function in this form is absent in my table. So the only way that I can do is to reform this into a form that I can see it in my table. And because my table is not that complicated right now, it doesn't include that many rows. So there is no guarantee that it's clear this shouldn't be this case, so I have to change it into this form. So what should I do? Okay, so what should I do? Can you help me to do that? Yes, Rocco?
Yeah, you can rewrite square root of x as x to the power of 1/2, and then you can just add 1 plus
Exactly.
1/2.
So that is the formulas involved. Let me write them. I really want you to memorize them. That's not hard. Of course, you can always only memorize this one. This will work for this one and this one as well. And then I want you to, of course, memorize this formula of the power rules, yes? Yes. These, by now, you should have them in your memory, yes? Okay, when the time is, okay, we have time. So, as Rocco mentioned, I will do actually the same. So the first thing is that I have a function, I want to differentiate, I do not have it in my table, I have to change the form of my function. So instead of x, I write x, the operation is here, the product, multiplication, and then I have x to the power of 1 over 2. But then this rule will help me to combine them into one exponent. So this becomes x to the power of 1, which is the exponent here, plus 1 over 2, and then it becomes x to the power of 3 over 2. Now everything is ready, yes? If I ask you, do you see this function in your table? You would say, yes, this is the second row. What is the corresponding value for little c? Is 3/2, yes? So then it means that I can start differentiation process right now. I couldn't start differentiation process in this form. I have to change it, and these are harder questions. These are E-level questions, and the questions that you have to manipulate it a little bit before starting the process are higher level questions. So what I do here, now tell me, what should I write for f prime of x? 3 over 2 will play the role of this little c, it should go down. Yes. So it becomes 3 over 2, and then what you write, x to the power of 3 over 2 minus 1. And then don't leave it. Differentiation is finalized here. Simplification is coming next. So 3 over 2, there is a better name. Instead of 3 over 2 minus 1, we can write
3 over 2 minus what? 2 over 2?
no.
1 over 2.
Okay, 2 over 2, the answer becomes 1 over 2, yes? So the answer is 1 over 2. Of course, if you want, you can stop here, but I myself prefer to write it back in the language of third sign. It's for us, it's easier to understand, but this is not a have to for this exercise. You can stop here, but I prefer to stop there. Yes? Is that clear? Any questions? Yes?
If you write it like whole numbers, like, not whole numbers, so if you write 1.5 instead of 2.5.
No, in that case, no problems. But if the fraction is a form that if you do it, you get approximations, then no, that is not allowed.
It's like a number.
In this case, yes. It's a whole number. Okay, I want to write one more here for you, and then wait for you, and then continue the lesson if you have more time. So number 4, this is easy, but you have to write it. So let me write f of x as x to the power of 2, the third root of x to the power of 2 multiplied by the second root of x. So that's the product between them. I pause the video. I want you to finalize this problem for me. Yes, if you can do it yourself, so whatever we discussed so far you have learned. Does anyone have the answer? Yes, Abdullah?
19 over 6 is to the power of 13 over 6.
Agree?
I got that, yeah.
Yes? Fine. So let us just do that, but I want to simplify it at the end, okay? And I will ask for the simplification. So here, what I do, I would write it as f of x equals to x to the power of 2. Then I have to use, I can always use this formula, yes? So here, n is 3, m is 2. So then it becomes x to the power of 2/3. And then the other one is x to the power of 1/2. And let me just repeat this once more again, even though I can take the derivative of each one of them using that formula, but don't do that because the whole expression is not in that form yet. Okay, so what I have to do, I have to write x, I have to add the exponents by this rule of powers. So this becomes this. And then you have to take the common denominator, which is 6. So this I would write it 12 over 6. This I would write it as 4 over 6. And then I would write it as 3 over 6. And then as you probably got, 12 plus 4, 16, 19 over 6. That is my function. And now, is my function in the form of in the table? Yes. C is played by this 19 over 6. So f prime of x is equal to 19 over 6 goes down, and then I will have x to the power of 19 over 6, 1 unit less. So then it becomes 19 over 6, x to the power of 13 over 6, yes, because 1 is 6 over 6. That is completely okay if you stop here, but let me try to learn how to write it as a third. So you can stop here. So let me change my color. It's not mandatory for this problem, but let us just do that. So here, if you want to, you can write it back in the form of a third sign. Okay, Robert, do you want to say?
6th power of x to the 13.
X to the power of?
13.
13. But still I don't stop here. I continue a little bit more because now I have an exponent which is higher than this root. So what can I do? I can write it as 19 over 6, and then I would write this. This one, it is x to the power of 2 to the power of 6, and then one more x. Okay, I want you to learn this trick as well. Why is that good? Because first of all, 2 times 6 is 12, and 1 is the same 13. But now this one and that one are the same. So x squared can be moved out of the third sign. So this becomes 19 over 6. X squared goes out. This will disappear. Under the third sign, I will have only x. For us, I would say this is easier to understand than the previous one. X to the power of 13 might be a very big number, but then you see x to the power of 2 and x are more manageable. And then this is, if I want to simplify it, I will continue until this one. And whatever I have written in green is not mandatory for this particular problem. Is that understandable? Yes? Okay. Now let me return to what we have started with. These are the type of questions. Let me see. Okay, let me also give you some one more example. I think here would be enough. Number 5. So what do you think would be f of x is equal to 1 over the third root of x to the power of 2. Okay, so let me give you time about this one as well.